Welcome to Data Skeptic Machine Intelligence, our podcast series exploring contemporary topics in artificial general intelligence and large language models. Large language models like ChatGPT are pretty amazing in their ability to solve countless natural language tasks, having no explicit prior training in those tasks. It is approaching something general purpose. And this general purpose nature has left a lot of people looking for new ways to get value out of LLMs in other tasks outside of language. Consider graphs, for example. When I say graph, I don't mean data visualization. I'm talking about nodes and the edges connecting them, like you'll find in a social network analysis. There's no shortage of problems graphs are used to solve. For example, consider telephone records where each phone number is a person, and each call is an edge between the two people that called each other. With just this data, a node classification task can typically identify things like if a phone is a business or personal line. There's also link prediction, which in our phone example would be trying to predict the likelihood a call will occur between two numbers. You can express problems like these in natural language sorts of ways, describing both the task and the data as well. Thus, you can convert from graph data to what format it should look like when being passed to the large language model. And that conversion process of going from graph data into some format that's text that can go into a large language model, that's a major part of our discussion today. But there's a few quick terms we used during the interview that I thought I should provide some definitions of. First, graph inductive bias. This is the idea that useful information can be learned from one graph and transferred to another. If we study the telephone records for only one city, it would provide a limited and somewhat biased sample when compared to the total population. However, a machine learning system trained on graph data achieves an inductive bias that might carry over into other problems that have similar structures. Of course, there are many different structures of graphs, and that can pose a problem knowing what domain can transfer to another one. That brings us to our two last definitions: homophilic graphs and heterophilic graphs. In homophilic graphs, nodes tend to connect like with like. This shows up to a certain degree in social network graphs, where friends connect with friends, and not too often with enemies or strangers. Heterophilic graphs have nodes much more likely to connect to dissimilar nodes, somewhat like the emails of a business in which peers send less emails to each other than they do to their managers or external customers. And with those definitions in hand, let's jump right into learning about GraphText. And thanks to our sponsor, Hex. You can learn more at hex.com/dataskeptic.
My name is Jianan Zhao, and I'm from Mila and University of Montreal. I generally enjoy doing research on graph machine learning and natural language processing, and currently I'm focusing on the interesting topic, graph foundation models.
And what first got you interested in these areas?
When I doing my master at BUPT, my supervisor introduced me to this graph machine learning area. I have been doing research since then, and recently I'm interested in the natural language processing and also the bridge of these two areas. Currently, I'm working on graph foundation models. I think it's a very interesting topic and have huge potentials.
Well, before we get into these contemporary kind of cutting-edge topics, I'm curious, is there any history to these fields? I've not thought of natural language processing and graphs as having all that much to do with each other. They're not totally foreign, but in most places I've encountered, people don't study both. Has there been a historical overlap, or is this a new emerging trend?
I think the historical overlap widely existed in both fields for a long time. For example, in natural language processing, the sentence have actually a graph in it because you have the subject and the object, and also how you organize the sentence is actually performed using a graph called lexical tree, which is how grammar forms. And also you have these connections between the documents or passages, and these relationships are also graphs. And in the graph field, this kind of relationship are built into text attributed graphs. In general, in natural language processing, there exists some graph structure in the sentence, and in the graph machine learning field, we can form special form of graph, like text attributed graph, where node features are text. So I think these fields are quite overlapped even before the graph foundation model, which emerged this year. I think the bridge, the connection between these fields are developing in a very fast pace.
Well, when I started learning about foundational models for natural language processing, it seemed like a really good idea to me because we're all speaking the same language. Maybe, you and I are talking about machine learning, and on some other podcast, they're talking about comic books, but it's all English in this case, and the sentence structures are the same.
Yeah,
But graphs don't necessarily have this relationship. A graph of a subway system might not be the same as a graph a biologist looks at.
yes.
What can we expect from a graph foundational model?
Currently, there is no a clear definition of a graph foundation model, but my understanding is that we can use a foundation model, one model for multiple graph tasks and on multiple graphs. That would be my definition of a graph foundation model.
And when you train it, is it fairly analogous to how one trains a large language model, or are there different techniques?
Yeah, I think that would depend on what kind of foundation model we are talking about, and also depend on what kind of scenario, like are we doing pre-training or fine-tuning or just doing the inference? That will be quite different.
So I've downloaded a few of these foundational language models, and to sort of give a general description of them, you put text in, and I can get either text out, or sometimes I want the embedding. I can just get a number out. What is my input and output when working with a graph foundational model?
Yeah, so the input of the graph foundation model is one graph or multiple graphs, and the output of the graph foundation model is like for node classification is the target prediction you would have for the model, and for graph classification it would be the class of the target graph.
So, one of the graph tasks I know about is predicting whether an edge exists or not. Maybe you are wondering if two nodes are connected and you just don't have that information yet. Are there some benchmark tests like that one that we would hope that these foundational models can take on?
I know a paper called GPT-4 Graph, which did the similar thing you talk about benchmarking. I think they've got the edge level tasks, but I think there is also one recent paper called Ultra, which is also a clear summation. You can take a look at that paper too. They've also have some knowledge graph reasoning, which is essentially link prediction you are interested in. They have also benchmarked a few against a few baselines.
So I've spent a lot of time interacting with large language models, and I'm pretty impressed with how I can give them a lot of different problems and they solve them. Like maybe a word problem from an elementary school textbook, and it'll figure it out. Or I could ask it to write a poem, and even though nobody explicitly built in poetry to ChatGPT, somehow it knows all the formats of the poems and it can do it. What happens if I present it with questions about graphs? No pre-training, just the raw language model. I say, here's my adjacency matrix, and I ask it a question. Can it do it?
In this year's New Rips paper called NL Graph, they just did what exactly you described. I think their conclusions are that natural language models, like large language models, they have some very limited reasoning ability on these graph problems, such as the shortest path distance. But I think the way that directly describe the adjacency matrix and also the like node attributes, this won't work well enough to solve real world problems. Like node classification, you got like a very giant graph. You cannot just fit this kind of large matrix into the context window for large language model. And also in the large language model distribution, they don't have seen such context of graph, so that they cannot do this task well. So that is my understanding of your question.
Well, if I were cynical, maybe I would say just be patient and wait till the context window is big enough, and maybe it'll be better.
Do you think that's a viable solution, or do we have to make our networks and kind of find a way to merge these two ideas and bake in graph aspects into language models?
I think context window is not a good solution because I think the effectiveness of graph neural network is to selective filtering the graph signals, which are the features of the graph. I think it's hard for large language model like you give them like 1,000 words, but only one word would predict whether the node is like machine learning paper or not. Without pre-training, I think only by prompting the large language models, this won't work quite well. I think a better way is to leverage some graph inductive bias to form a shorter but more informative context for graph, like what we did in the GraphText work. And the large language model will simply select from the informative ones and form their decision. I think this is a better way to do this.
This episode is brought to you by Hex. You're a data person. You probably have to jump between different tools to run queries, build visualizations, write Python, and then send around a lot of screenshots and CSV files. Hex brings all of that together. Its powerful notebook UI lets you analyze data in SQL, Python, or no code in any combination, and works together with live, multiplayer, and version control. And now, Hex's magical AI tools can generate queries in code, create visualizations, and even kickstart a whole analysis for you, all from natural language prompts. It's like having an analytics co-pilot built right into where you're already doing your work. Then when you're ready to share, you can use Hex's drag-and-drop app builder to configure beautiful reports or dashboards that anyone can use. Join the hundreds of data teams like Notion, AllTrails, Loom, Mixpanel, and Algolia using Hex every day to make their work more impactful. Sign up today at hex.tech/dataskeptic to get a 30-day trial of the Hex Team Plan. That's hex.tech/dataskeptic.
So would it be correct to say that GraphText as a framework translates graph data into natural language as like a pre-processing step?
Yes, I think you are correct. Yeah.
And could you describe a little bit about what the translation results look like? Is it human readable in any way?
Yeah, it's human readable. The translation is based on a tree. You know a tree has some structure like hierarchical tree structure, and also the traversal of the tree forms a text. Like many text data are in the tree format, like the web page. It's actually a DOM tree in the XML format, and code data is also hierarchical tree data. And when we translate the graph data to a tree first, and then we flatten them using the traversal, like depth first traversal, and the resulting sequence is actually some kind of like XML data and JSON data, which large language model have seen a lot in their pre-training distribution. So that not only humans can easily recognize the hierarchical structure inside the translated graph, but also large language model can reasoning on it.
Well, all trees are graphs, but not all graphs are trees. Do you lose anything in the translation process?
That's a very good question because when we design our tree, we just not we did not use all the information that a graph provides, but instead we use subgraph of the entire graph. So absolutely there is some information loss here. But what we want to do is that we use the inductive bias of graph, like the inductive bias of GCN is to average only their neighbors, and JT is to average their neighbors with similar features. We can construct our tree with this inductive bias so that the information loss is not that much and the useful information is obtained. Actually, I don't think the information loss is a bad thing. So if you lost some noisy data, like in the previous example, I've mentioned that if you have like 1,000 words, if you filter out the useless like 999 words and leave only the one word, it will be a much simpler problem for the large language model to predict.
Well, I think anyone who knows about graphs knows that they are nodes and edges, and they can be described in a lot of ways, such as the graph text translated output. But sometimes there's more to a graph than just its nodes and edges. If I was doing something like a roadway analysis, maybe I want a property of the node that tells me what kind of intersection it is. How can your approach manage these additional values?
In GraphText, we didn't dive into the edge attributes, but I think there is always a way to incorporate them in the tree. For example, you can add the attributes to the edges in the tree so that when you traverse the tree, you can put them in the text.
And if I were to take some of my graph data and use graph text to translate it, I get that new representation. Can I just copy and paste that into ChatGPT, or do I need some additional steps?
Yeah, you can definitely do this. In fact, all of our experiments on in-context learning is just like what you described, except we call the ChatGPT API, which is quite the same.
And now you've invented sort of a new schema here in GraphText. There are existing approaches, I'm sure. I don't know any off the top of my head, but there must be like an XML way to represent graphs and probably some custom formats. And maybe ChatGPT knows a little bit about those. Why invent something new?
Because the existing work of XML are mostly based on the raw graph, which I have mentioned are noisy and very large. And our work provides the way to construct a tree. And using a tree as an intermediate, we can just design how we can incorporate our graph inductive bias so that the output text of the graph is more informative than the previous like graph ML work you mentioned, which is also XML based. We also have some recent experiments on this kind of work that's showing that using this original graph to construct a XML is not as effective as ours.
And let's imagine I have a big graph, like something I got out of the OpenStreetMap, and it's all the kind of connections of highways and roadways and whatnot. It's too big probably to translate and put into the context window. What do I need to do if I'm working with a really, really large graph data structure?
So, what task are we specifically talking about, like node classification or link prediction?
Oh, that's a good question. Let's go with either one you think is a better example.
Okay, so if we are doing node classification, maybe we can just predict the role of the each spot connected with by roads. So if you think the task can be solved by a GNN, which the inductive bias is the message passing, we can just simply perform message passing using the non-parametric way, which you propagate the feature several times. Like if you think the two hop features are relevant, you just do neighborhood propagation two times. Like you multiply the feature matrix with the adjacency matrix two times, and you got this propagated feature. And then you just convert them to text. It's quite simple. Like you can just do a clustering on this propagated feature. Then you got the text cluster index for the target feature, which is the propagated feature you want, and then you construct a tree with those features. And how do you construct a tree is now we have the feature, and you need to determine what kind of relationships or the edges in the tree you want. Maybe you want the two hop neighbors, and then you take their propagated feature to construct a tree, and then finally you flatten the tree using the dispersed traversal, and you got the text you want, and you can feed this to ChatGPT to ask your question.
Well, I really like the framework we've been describing, but how can we determine if it's effective or not?
So we have derived several experiments on both homophilic and heterophilic data and on node classification. So what we observed is that our work has quite amazing performance, especially on the few shot settings where only few label nodes are observed, and we can sometimes surpassing existing state-of-the-art GNNs like GET V2 and GCNII. Another remarkable aspect of our framework is that we can let the language model to reasoning in natural language, and so that the output is human readable and interpretable. And you can easily decide why the language model are wrong or correct. And then you can refine their answer by providing feedbacks, and they can actually refine their answer accordingly.
When you conduct experiments, and you mentioned that this approach performs pretty well, could you describe like maybe the raw data and what the challenge is?
Yeah, so the raw data, like we use standard node classification data set like Cora sets here, and also some heterophilic data set like Texas, Wisconsin, and Cornell, which are web page data. And Cora and Sathir are citation graphs. The target of this task is to predict the class of the nodes. Like in Cora and Sathir, the target is to predict the category of the paper. And in Texas and Wisconsin and Cornell, the target is to predict the row of the web page.
Well, if maybe we zoom in on Cora and Sightseer predicting the category a paper could go in, I suspect if you asked maybe 20 experts in the field, you might get two or three different answers. You know, something from one perspective could be a computer science paper, from another perspective, it's a statistics paper. You know, there's overlap between fields, so there's no real ground truth except for where the author happened to place it. I guess what I'm trying to say is that there's a variance to some of these problems. Do you measure it against like a human performance or what's your baseline?
So the baseline is actually most GNNs. And I think you are correct that, for example, in science theater, there is a class called artificial intelligence and also a class called machine learning. So these are quite the same. But we did not let humans evaluate these kind of things because the data we are using are actually processed, like in the raw GCN paper. And we do not have the text feature of it, so it's undoable for humans to evaluate such things.
And for your results, how do they compare to graph neural networks that are trained specifically for these purposes?
The standard graph neural networks like GCN and GET, and also their ablation GCNI and GCNV2 are what we compared. And they are performing quite well on these datasets, especially the homophilic datasets like Cora and Sathir. On Texas, Wisconsin, and Cornell, which are heterophilic, which is against the standard message passing's inductive bias. In these data sets, the higher order neighbors, like two hop neighbors, are really important so that the GNNs are not performing very well. And we are surpassing them on these data sets in some cases. And on Cora says here, we are not outperforming these baselines. But however, I think the performance of ours are better than some heuristic-based baselines like label propagation, which proves the effectiveness of our model. And also, our model is not trained. We just use the inference of ChatGPT. And all of the GNN baselines needs to be trained, especially for each data set.
Yeah, it's almost surprising that your approach could be competitive because it's not really doing anything graph specific. It's just relying on the power of the large language model in a sense.
Yeah, thank you.
Do you think that there is a value in combining the two approaches? Could it become even stronger with a hybrid method?
Yeah, I think you are correct because in the text attributed graph I've mentioned about, which nodes have text features, large language models are really useful if we augment the feature. For example, in the recent paper called Tape, the paper title is the explanation as feature. We can use a large language model to predict papers category based on their title and abstract. And then this kind of generated text can be used as feature to further boost the performance of GNNs. So this is one term of combining both large language model and graph neural network.
Well, if you're going to rely on something like ChatGPT or a large language model as part of your pipeline, you're also then at the mercy of what the model might do.
Yeah,
For example, I often, well, not often, but I sometimes find that I bump into refusals where the system says, "I can't help you" or "I won't help you" for some reason. Have you faced challenges like that?
I don't think our in our we have experienced such issues, because what we are asking is let them simply predict the labels of a paper. Like the context they are dealing with is mostly like primary school level. So there is no such maybe internal alarm is launched in the large language model to prevent them from generating answers.
Well, one of the strengths of the GraphText approach is that it has some interpretability or at least explainability components and this, what you describe as interactive graph reasoning. Could you expand on that a little bit and talk about what it's like to participate in the interactive graph reasoning?
So when you construct a tree, you can add the relationship as the text. Like for center node, you can add the center node to the graph prompt, and the personalized page rank based neighbors, you can tell the language model that these are a personalized page rank based, and let the language model decide what kind of information they need, the Sentinel feature or the personalized PageRank feature. Like in our example, we show that in some cases, Sentinels are not as good as personalized PageRank labels. Especially, it can be concluded in the demonstrations. So what we want the large language models do is that they can fix their inductive bias that Sentinel are more important, and decide that the personalized page rank is actually more important. We can just tell them that what personalized page rank is, which reminds it of it is related to the graph, and also it's a sequence. It's a neighborhood sequence that the first is the most crucial, and that the language model to reevaluate their prediction. With this hint and of human interaction, that large language model can finally refine their previous belief that the center node is more important. So this is a complicated example, but I hope it answers your question.
If there are any listeners who wanted to try out GraphText, how would they go about it?
Like they can take our code and convert their own data set to the format that we have processed, and then they are ready to go. Or simply they just construct their own tree based on their inductive bias and send it to ChatGPT in their web page. I think it's quite simple. Yeah.
What's the future of GraphText? What comes next?
One of the work is that we can make instruction fine-tuning work, but in our paper we did not quite make that work, and we spend a lot of time on instruction fine-tuning. Basically, we just want the large language model to understand the graph's data and update their pre-training distribution. But the results we are getting is not outperforming existing graph neural networks. And also, I think the graph reasoning here we are doing is mostly benefited from the graph inductive bias we have talked about. And the large language models are actually not performing quite graph reasoning. They are just using their graph previous belief that like sentinels are important and what personalized page rank is. And the actual thing they are doing is like majority vote and like lookup function or just linear map. For example, map the one type of feature to a specific label. I think it is not good enough for a large language model, because we all know that they are very capable of doing complex things. So that would be interesting future work to let large language model reason well enough. Perhaps we can do some chain of thought reasoning, like multi-agent collaboration, to achieve complex reasoning on graph.
Well, large language models are impressive in lots of ways, but then they're surprisingly dumb in other ways. I see them fail at simple things like counting words or even basic arithmetic. What do you think about the architecture? I guess the transformer specifically. Is that the right tool for being able to reason about graphs? Or will we eventually need like a graphs coprocessor or subnetwork or something like that?
Yeah, I think that's a very good question. I think one core question for designing a graph foundation model is determining the backbone model. What do you want to use, like graph transformer, graph neural network, or just pure transformer decoder like GPT? There have been many attempts on either model, and I think some of them are quite successful, especially large language models based. If we are looking at inference only, and graph neural network based if we are looking at fine-tuning a model. The core advantage of using graph transformers and graph neural network is that they have the built-in inductive bias that we want to do message passing that aggregate neighborhood information. And for transformers, it has less inductive bias, especially on graphs, that all neighbors are viewed equally and compute their attention scores. This might be an advantage in natural language processing and computer vision, but I don't think that would be a final solution in graph. So personally, I'm more biased toward the graph neural network based as a backbone for graph foundation model than the transformer decoder based.
Well, I think it's a very exciting time to be an NLP researcher and or be a graph neural network researcher. Are there any hopeful, optimistic, maybe futuristic thoughts you have about where the field's going? What might we see in the next couple of years?
One direction is to migrate what large language models do in the natural language processing field to the graph field, like multi-agent and chain of thought reasoning. Another direction is to go beyond the graph community to a more general geometric community where the graph is as a special case of the geometric data. One specific example is like molecule representation learning. For example, molecule can be viewed as a graph, but the connections between the nodes have some 3D properties like chemical properties, chemical bonds. And how do we convert such data to one-dimensional sequence for a large language model? I think that's a critical problem because if you naively flatten them to a sequence, it will lose some property, such as the smells of a molecule will lose its 3D property. And currently, some works are based on smells. One interesting direction is to design a language for more general data than graph, like geometric data, and then to perform pre-training foundation model for this kind of data and improve the fine-tuning performance of the downstream task.
And is there anywhere listeners can follow you online?
They can follow me on Twitter, and also I have a homepage and a GitHub account.
Sounds good. We'll have links to all of the above in the show notes for listeners who want to follow up. I want to thank you so much for taking the time to come on the show and share your work.
Yeah, thanks, Kyle.